안녕하세요. 저는 김화기술의 김태수 부장입니다. 오늘 웨비나에 참석하여 주신 모든 분들께 먼저 감사의 말씀을 드립니다. 오늘 웨비나에서는 불확실성 정량학 분석 및 가시화 기술과 관련하여 설명을 드릴 예정입니다. 그리고 오늘 웨비나 강사로 스마트 UQ사의 개빈 존스 씨가 참석하고 계십니다. 개빈 존스 씨는 스마트 UQ사의 수석 어플리케이션 엔지니어입니다. 에어로스페이스, 디펜스, 오토모티브, 가스터빈, 의료기기 등 여러 산업 분야의 시뮬레이션과 통계 작업을 담당하고 있습니다. 또한 스마트UQ의 디지털 트윈 디지털 스레드 이니셔티브의 핵심 기여자이기도 합니다. 위스콘신 대학교 메디슨 캠퍼스에서 엔지니어링 메케닉스와 애스트로노틱스 그리고 수학을 전공하셨습니다. 그럼 스마트UQ사에서 준비한 웨비나 진행을 위해 부탁을 드리도록 하겠습니다. 만약 접속에 지금 장애가 있으시거나 중간중간에 어떤 이슈가 있으신 분들은 채팅창에 저희가 help@kimha.co.kr 이메일을 남겨드렸으니까 김화기술에 이제 도움 요청을 남겨주시면 감사하겠습니다. 그러면 좋은 웨비나 시간이 되시기 바랍니다. Okay, Gavin, I just finished a short introduction, including information for instructors' background information. So, would you now take it back and proceed the webinar?
Okay, thank you very much.
Thank you.
So I'll just begin with a very short overview of SmartUQ as a company if you're not familiar with us. So we're a machine learning and uncertainty quantification company. We're based in Madison, Wisconsin. The primary product we do offer, though, is the software package SmartUQ, which is, of course, going to be a focus of the webinar today. So in terms of SmartUQ as a very initial high-level look at the features offered, I'd say there's three main categories of tools within SmartUQ. So there's designs of experiments and data sampling tools. So those are to decide which data to collect or use. There's a variety of predictive models. Sometimes people will call the predictive models machine learning models or surrogate models or emulators, but whatever you call them, just different models you can train using the data. And then lastly, there are the analytics features. So lots of times this is going to be analyses we can perform using the predictive models we trained in, say, the second category of tools. So we're going to go through all of this in a lot more detail. We know all these features, of course, as we go through the webinar, and we'll compare and contrast, what SmartUQ offers here to what JMP or JUMP offers in these various categories. So for an overview of SmartUQ as compared to JUMP to start with, just a high-level review of that. SmartUQ and JUMP or JUMP Pro as well can be complementary tools because they're really designed for different purposes. So there are some SmartUQ customers that use both tools. SmartUQ, we were invented to solve complex machine learning and uncertainty quantification problems. So we got our start with problems in jet engine and gas turbine applications. It's a tool that's very well suited for machine learning and UQ applications in a lot of industries as a result. We've designed SmartUQ basically from the ground up to make it easy for practicing engineers to use advanced statistics. And part of that is that we have a very user-friendly graphical user interface or GUI that you'll see as part of the demonstration today. But we do also have a Python API that users can make use of to incorporate our tools and features in code in Python scripts, for example. We're primarily focused on, machine learning, uncertainty quantification, probabilistic design and analysis, and we're also kind of continually working to invent and implement new methods and algorithms. So to do things like more intelligently sample big data, improve the training speed and accuracy of our statistical modeling techniques, and handle new and challenging problems. Now, by contrast, JMP or JUMP and JUMP Pro have more standard analytics tools for engineers and scientists. For instance, in general, JMP is going to have more traditional design of experiments generation tools than SmartUQ, but only basic machine learning models or meta models or capabilities in that area. I do apologize. I've had a bit of a cold, and as I'm talking here, I'm losing my voice a little bit, so I hope I'm not too difficult to understand, and I might need to pause here and there just to get a sip of water and clear my throat. So if there is a pause, I apologize. That's what's happening. So the specific topics we're going to cover and do the compare and contrast to JMP and JMP Pro are going to be first with design of experiments. We'll talk about data sampling, which is a more unique feature to SmartUQ. Then we'll talk about the comparison of the different predictive models. We'll talk about model calibration, which again is unique to SmartUQ. That has more to do with getting simulations to agree better with test or experimental data. I'll actually do a demonstration of our frequentist calibration tools as part of that. We'll talk about inverse analysis, again, a unique feature to SmartUQ, and then we'll conclude with a comparison of just other analytics that SmartUQ has and a more in-depth discussion about some of its integration and automation features. So starting with design of experiments, as I mentioned a couple slides back in the overview, for design of experiments, JMP is going to have more options for traditional DOEs, but SmartUQ has a greater variety of options for modern design of experiments. So for example, both SmartUQ and JMP have Latin hypercube designs or LHDs, but SmartUQ has more options for optimizing those LHDs. We have a number of variants on LHDs like sliced and nested designs. We have more efficient LHDs. You see a quote from a customer there talking about SmartUQ creating a large design much more quickly than JMP. And we also have, more modern designs in general. So things like sparse grids, hybrid designs, designs for calibration, constrained designs of experiments, sliced and nested structures for all those as well. So on the other hand, for traditional design of experiments, SmartUQ and JMP both have factorial and fractional factorial designs, but JMP has additional traditional designs like de-optimal designs and response surface designs. So SmartUQ has unique tools for data sampling that JMP and JMP Pro don't have. So these tools are designed not to decide which data to collect, but when you have existing data and you're trying to extract maybe a smaller representative subset from that larger data set. And perhaps you want to use that smaller data set to have, a more efficient set for training a model, for instance. So data sets of this sort we tend to find are more common in cases where, maybe you're collecting data from, say, high frequency sensors or something like that. So I have an example data set here I want to use to illustrate SmartUQ subsampling. So in this case, we have a robot arm. The robot arm has 7 joints. Each of those joints has a parameter associated with it that gives its position, its velocity, and its acceleration. So in total, the behavior of the robot arm is characterized by 21 total input values. So for a set of those values, the position, velocity, and acceleration of each joint, the data from the robot also tells us what the torque is in each joint. And in total, we have data collected from this robot as it, performs its standard operations, and we have around 45,000 data points for that. So there could be, certain actions the robot performs very often. There could be other actions that are more rare for the robot to perform. So there might be a lot of redundant information in this data set. So if we're trying to reduce the size of this data set and pick a small sample of it, randomly picking a small sample might not be a good approach. If there's important information, maybe the rare activities the robot arm undertakes, have very high torque values or critical cases we want to be studying, we want to be exploring. We don't want to miss out those cases by randomly picking from this data. So that's where subsampling can come into play. We can pick a small sample of this data, but that will, as best as possible, cover the full input space available. So we'll compare basically 1,000-point sample of this data taken at random to 1,000-point sample taken SmartUQ's subsampling way. So we start here with a visualization showing the full input space. So these are all the two-dimensional projections of that 21-dimensional space. And we can see as well here those same projections, but just for the 1,000 points or so taken randomly, and the ones sampled according to SmartUQ. Now, this is a lot of projections. Everything's kind of small. So for the sake of illustration here, I'm going to zoom in on just one section here. We can see that, these projections have some characteristic shape, some characteristic behavior to them. For instance, we have this one projection kind of has a heart shape to it. So in the randomly sampled data, we can see that it's not doing such a good job of representing the input space fully. This left lobe of this heart-shaped region is fairly sparsely populated as compared to the actual data set. This upper left projection, you can see it's a lot more narrow than in the full data set. If we look at the SmartUQ subsample, we can see that it does a much better job of representing the original data. So we see that this heart-shaped region, both lobes are more fully characterized. This upper left projection has more of the full width of the original data. So again, we're getting a better representation of all of the input conditions that existed in the original data set than if we had used a smaller sample. So what are some of the effects that better sample can have? For one case, it could be, when we look at taking that data to train a model. So we compare training models with the randomly selected data to training models with the subsample data. And depending on which of the outputs we're trying to predict, we get a different result. But, in general, we're getting somewhere between 20 and 40% better accuracy with the data selected using SmartUQ. The flip side of that would be that, if you had a specific target accuracy, you could achieve that with less data. Another tool SmartUQ has that's unique, similar to subsampling, is something we call data slicing. So whereas subsampling extracts a single representative subset from the larger data set, slicing divides the data set into a user-defined number of representative sets, which we just call slices. So as I mentioned in my overview, JMP has some basic machine learning modeling tools or meta modeling capabilities. But one of the key strengths of SmartUQ is the variety and the performance of our options for predictive modeling. So on this first slide here, I'm going to focus specifically on Gaussian process modeling techniques, which both JMP and SmartUQ offer. And then I'll move into other techniques in the coming slides. So for Gaussian process models, SmartUQ has models that train much more quickly and with better accuracy than not just what is available in JMP, but then Gaussian process models, however they are traditionally implemented. But as compared to JMP, we can see some examples here of, for a given data set, it taking 3 days to train the model in JMP and 3 minutes to train it in SmartUQ. The other thing that makes SmartUQ unique with respect to Gaussian process models is that JMP with Gaussian process modeling can only handle problems that have inputs that are either continuous or potentially discrete or categorical, although for discrete inputs that requires Jump Pro, and continuous outputs. Whereas SmartUQ has a lot of additional unique Gaussian process modeling variants we've developed that let us handle, with the benefits of Gaussian process models, problems where there is discontinuity, for example, in the response behavior, discrete response behavior, outputs that are spatially or time varying, outputs that are maybe binary in nature. So rather than the output being a numerical value, it might be a pass-fail value, for instance. So another capability that you can have in SmartUQ with the Gaussian process models is that Gaussian process models, if you're not familiar with them already, produce a variance prediction. So they make a prediction of the output, the value we're trying to predict, but they also give a prediction that we call variance prediction, which is basically a measure of the uncertainty we have in that predicted value. So that variance prediction can be used to put confidence intervals around the predictions we're making, for instance. So we have a tool called adaptive design in SmartUQ that makes use of that variance prediction to understand where the model is, least confident in the predictions it's making. And then that information in turn can be used to suggest to the user where they should collect subsequent data to have the biggest effect on improving the model accuracy. So it's a technique to help minimize the amount of data that needs to be collected. So on this slide here, we'll talk more about the non-Gaussian process-based modeling options that are available in both JMP and SmartUQ. So both JMP and SmartUQ have a number of options that are in common. So they both have linear regression models, response surface models, neural networks, support vector machines, although that's only in Jump Pro. And then both SmartUQ and Jump do have a couple model types that the other does not have. So for SmartUQ, the models that are not available in Jump would be things like radial basis functions, generalized additive model, polynomial chaos expansion, stochastic collocation. And in Jump, the models they have that are not offered in SmartUQ would be linear mixed effects models, nonlinear regression, and decision trees, although again, that would be only for Jump Pro. So one additional category of features that SmartUQ has that is not offered in JMP is in the area of model calibration. So in general, model calibration is going to be for helping to get simulation models to agree better with experimental or physical data. It could also have applications to getting lower fidelity, cheaper to evaluate models to agree better with more expensive, higher fidelity models. I'm going to stick in my explanations here, though, to the idea we have a simulation and we would like it to agree better with test or experimental data. So the best place to start that discussion is with why a simulation might not agree with physical data in the first place. And one reason a simulation might not agree with physical or test data is due to parameter uncertainty. So within our simulation, there's a number of parameters we're free to choose values for. So things like heat transfer coefficients, stiffness and damping coefficients, turbulence model parameters, material property parameters, and so forth. And depending on how we pick those values, of course, a given simulation result is going to give a different result. And in turn, that's going to, agree more or less well with reality. So there's a question here of parameter uncertainty. Basically, what is the best choice to make for those parameters in the simulation to get it to agree with the experimental data as well as possible. When we construct the simulation, we also make some assumptions, we make some simplifications, and those are going to introduce uncertainty and disagreement with experimental or test results. And it's possible that if we make assumptions that are oversimplifying or maybe incorrect assumptions, that's no matter how we pick the parameters in our simulation, we're not going to get good results or results that agree well with reality. So there can be a relationship between the model form and parameter uncertainty. So for calibration, SmartUQ offers a couple options. We offer a data matching calibration. This is a method that only addresses parameter uncertainty. This is basically an optimization approach to tune the model to find the best choice for those parameters. So as I mentioned, JMP or Jump Pro don't have calibration tools of any sort. Other software packages, if they do offer something along the lines of calibration, it would be more along the data matching type of calibration. Where SmartUQ is unique as compared to JMP and also any other software tools that are out there is with our frequentist and Bayesian calibration tools. So these are tools that address both parameter and model form uncertainty. The difference between them is that the frequentist tool is going to, for every parameter, find a specific value that works best, as with the data matching approach, whereas Bayesian calibration is going to find a number of different combinations of those parameters that all work equally well at agreeing with the experimental or test data. So in that regard, you can think of the Bayesian approach maybe more as a parameter uncertainty reduction technique. So a natural question might be, well, why are there going to be a lot of different parameters that, are the correct answer to use in my simulation? And one reason for that might be one of the sources of disagreement between simulation and experiment that I have not mentioned. And that might just be that the data, the experimental data itself, is noisy. So I run my simulation for a given case. I conduct the corresponding experiment. I get a certain value for that experiment, and that agrees to some degree with my simulation. And the amount that agrees with my simulation just depends on the random chance of what result I happen to collect for that experiment when I conducted it. I could have gotten a different value and in turn a different level of agreement, if I'd conducted the experiment, an hour later when the ambient temperature in the room was slightly different or something, whatever happens to affect the uncertainty in those experimental results. So if the experimental result by chance had been slightly different, there would have been a slightly different choice of parameters in the simulation that would have been appropriate to give, the closest agreement with that. So before I get into a demonstration of calibration in SmartUQ, a demonstration of the frequentist calibration, just want to give a little slightly more background on how the calibration is done in SmartUQ. Don't want to go into too much detail, but this level of detail should be useful for understanding what we see in SmartUQ. So the basic idea is that when we do frequentist calibration in SmartUQ, we're going to train two machine learning models. The first model is going to be trained of the simulation. We're going to use that in basically a data matching optimization. So let's just find the best choice of parameters first. And then once we've done that, we're going to train a second model. We call this a discrepancy model. It's a model that's going to try to predict the remaining disagreement between what that first model predicts and what happens in reality. So that second model, that discrepancy model, you can think of it as something that, you can add its prediction to the first model's prediction as a correction factor to give you a prediction of what is most likely to happen in reality. But that second model, that discrepancy model, is a model like any other model in SmartUQ that you can run analyses on and do visualizations of. So you can also use it as a tool to potentially investigate the sources of model form error to improve the underlying model, for instance. So the data set we'll look at here, the example problem we'll look at for the calibration is this simulation of a bridge, simple problem, a FEA model of a bridge, structural simulation. So we have some inputs to our simulation that basically govern the dimensions of the bridge. So things like length, height, width, thickness of the concrete, and so forth. There's an input here that tells us what load is going to be applied to the bridge. But then we also have some parameters here that give us properties about the materials that the bridge is constructed of. So things like the Young's modulus value that we're using for the concrete, the steel, and the aluminum. So for a given bridge design, a given choice of those material property parameters, a given loading, we can run this simulation and it'll tell us what the maximum stress in the steel components is and what the maximum displacement of the bridge is. And in terms of a calibration example here, what we might want to calibrate is those material property parameters. So we might be able to run our simulations. We might have some test or some experimental data. And we want to find, what is the best, say, Young's modulus values to use in our simulation to get the closest agreement with what happens in reality. So I'll switch to SmartUQ now. We'll take a look at the data. So the first file I have here labeled bridge LHD, this would just be a Latin hypercube design generated in SmartUQ, telling us which simulations to run for our bridge. Then the bridge results is the results of those simulations after they were run. And then the file I've labeled physical inputs. This would be our test or experimental data. In this case, we mocked up this data, but in practice, this would be actual physical data. You can notice, obviously, that this is a lower dimensional data set than the simulation data set because, of course, here we don't have any input information for the parameters we're trying to calibrate, those material property parameters. And then for the physical outputs, these would be the results of these physical simulations. So here we will go to calibrate. In SmartUQ, we'll select frequentist calibration. If we had already trained a model of the simulation data in SmartUQ through, for example, the emulate menu here, we could just plug that directly into our frequentist calibration with simulation emulator tool. But here we will do everything from scratch. So in terms of, ease of use here, it's very easy to load the data. So I just select my simulation data inputs, select the outputs for those, and the physical inputs, physical outputs. So here I had already kind of pre-split everything up into individual files. That was in part for ease of explanation, but that doesn't need to be the case if you had, all of your data in a single file. You can either, tell SmartUQ which columns the relevant data is in, or you have a drop-down menu where you can drag and drop and select by column name. I'm going to select as our calibration option here, universal. Basically, I am trying to get one solution that agrees as well as possible with both of the outputs, as opposed to two separate solutions, one that agrees as well as possible with each individual output. In the interest of time, I'm not going to go through all the options here in detail, but effectively we pick an error type, which is, we're telling SmartUQ, what do we mean when we say we want our simulation to agree well with our test data? If when I say I want my simulation to agree well with test, what I mean is that, whatever the worst prediction my simulation makes with respect to test, I want that to be as small as possible, then maybe I want to define my error as maximum error. Otherwise, if I'm just looking for, across the board, my simulation to agree as well as possible with the test data, then maybe I want to pick something more like the default of sum squared error. This is effectively the objective function. You're defining the objective function here for the optimization that's going to be run. Also, choice of optimization algorithm to use for that. And as I mentioned in my description in the slides, there's two models being trained, the simulation model, the discrepancy model. So you have a different choice of settings, different types of models you can pick, and settings for those models for each piece. So the calibration completed here. We have the model trained of just the simulation data. We have the discrepancy model, but I think most interesting to look at here is just the combination of them, the final calibrated model. So for one thing, we can look at the calibration parameter tab. This tells us the choice of parameters that was determined to be the best to use. We can look at the multi-view as well. For simplicity here, let's look only at one of our outputs. And I'm going to remove some uncertainty propagation information for now. So effectively what we see here is the first row of plots is telling us the behavior, the response of the simulation only. So this is the model we trained of just the simulation, but after we have calibrated the parameters to it. So this has the parameter values, the best parameter values locked in. So this is effectively our simulation model with the parameter uncertainty eliminated. The second row of plots here is our discrepancy model. So this is telling us, the correction factor that we need to add to the first prediction to get the prediction that is most in line with what happens in reality. And that is the third row of plots. So this third row of plots is just the sum of the first two. As I mentioned as well, though, obviously we can use this, final prediction here to make predictions, to run our analyses. This is just a combination of a couple of models that predicts very quickly. So we can do all the regular next steps that are offered in SmartUQ, some of which I'll show in more detail coming up here shortly. But we can also just look at our discrepancy model and use that as a tool to investigate sources of model form error, try to understand maybe why our simulation doesn't agree as well with reality. So for instance, maybe if we're looking at a case like this, we can see here if the design is, as I've laid it out here, that our discrepancy model is tried to make it give a prediction value here as close to 0 as possible. Can't just moving my mouse, I can't get it much closer than that, but effectively this is predicting, 0. So it's saying, you don't really have to add anything to this first model's prediction. It's basically saying there's no model form error. The only uncertainty in the results is parameter uncertainty. You pick the right parameter values in the simulation, you get a simulation that tells you exactly what happens in reality. But we can look at this and we can see that, as we increase this parameter, as we increase the loading that we're applying to the bridge, our discrepancy model is predicting a larger and larger value. So this basically means that, as we increase the load that we're simulating, there's something in our simulation that makes it such that the result is going to increasingly underpredict what happens in reality. As we increase this load, we have to add a larger and larger value to that simulated result to get what happens in reality. So we're increasingly underpredicting the result. And, that could spark some intuition, in the engineer, in the person that's, working on this problem. What assumptions did we make in the underlying simulation that might lead to behavior like that? And perhaps you can go back and improve the underlying model. So another unique tool in SmartUQ that isn't available in JMP is something we call inverse analysis. So inverse analysis is used to basically characterize uncertainty for what we call unobserved inputs based on observed outputs. So you have, physical data, and maybe you can record, the results, the experimental results, but you don't know much about the inputs that lead to that results, and you're kind of trying to back out the input uncertainties that led to those observed outputs. That's something that inverse analysis could be used for. So in the remaining time here, we're not going to, be able to cover everything that SmartUQ has to offer, but I do want to finish by touching on a couple other similarities and differences between the analytics that SmartUQ and JMP allow users to perform on the models that they've trained. So SmartUQ allows global sensitivity analysis for problems that either have, continuous outputs or functional output. As I think I mentioned before, JMP doesn't have models that are going to predict functionally varying outputs. So of course, they're not going to be able to have sensitivity analysis, global sensitivity analysis for those sort of functionally varying problems. SmartUQ and JMP, though, both do have tools to visualize local sensitivity analysis. I didn't spend a lot of time describing that multi-view because presumably if you're viewing this webinar, you might already be a user of JMP. And so that visualization, that multi-view should be already very familiar to you. For uncertainty propagation, SmartUQ and JMP both have tools for that. We both do aleatory uncertainty propagation. So basically cases where your input uncertainties are characterized by probability distributions. But SmartUQ also can handle cases where you want to treat some or all of your input uncertainties as being epistemic. SmartUQ also has a lot of options for optimization, whereas JMP does not have optimization tools. So we'll take a look at a couple of those coming up here, but we have tools for your standard kind of deterministic, but also multi-objective, stochastic, reliability-based, and dynamic optimization techniques. So let me switch back to SmartUQ here. And we'll make use of the calibrated model we trained here. So we calibrated this model, and now we can run analyses on it. So I think probably the most interesting thing to look at, because there aren't any equivalent features in JMP, would be some of the optimizations. So we'll take a look maybe at the stochastic optimization. So we could do let's look briefly at the regular. So a more standard optimization. Maybe we're trying to find the design that minimizes the stress in the steel, minimizes the displacement. Maybe we have some other constraints. We could of course do this in SmartUQ. We could do it as a multi-objective optimization. So if we want a list of Pareto optimal points that try to achieve both of these objectives, that's certainly something we can do. What's maybe more interesting, though, is to think about cases where we want to handle uncertainty in some of these inputs. So you'll notice, load is one of our inputs. Maybe we're not designing, or, we can't necessarily design for a very specific load, right? We can't run an optimization that says, give me the best bridge design that's, minimizes these values and tell it to me in terms of a specific load. We can maybe have a range of loads that we're willing to, have the bridge support, and but we can't have, a single value, here's the best bridge design, and only let this one specific load be applied to it, and, then the design is perfect. So in a normal approach, how would we handle that? Well, we would, maybe have to run a deterministic optimization like that, and we would fix our load to maybe a worst case scenario, where we would have to fix it to like its mean value. or something along those lines. Stochastic optimization lets us handle something like uncertainty in one of the inputs as part of the optimization process. So we could switch our loading to a stochastic variable, and whatever distribution we want to give to the uncertainty in the loading, we could provide that. And now we're going to get a solution to our optimization problem that gives us the best design, to achieve our objectives here, but taking account the uncertainty we're going to have in the loading. We could go a step further in this, and we might, know that there are certain, manufacturing uncertainties that exist. We are going to, run an optimization. It's going to tell us a very specific diameter to use for the aluminum beams, but, we're going to source those aluminum beams from somewhere, and those aren't always going to have that exact diameter. As part of our optimization, if we wanted to, we could incorporate that into the solution of the problem. So again, I'll just kind of pick default values here, but the idea would be, find me the design that, minimizes the stress, minimizes the displacement, given the uncertainty we have in the load and given the uncertainty we're going to have in terms of manufacturing that design that is provided. We get a result here, and I guess here I failed to switch it to a combined optimization. So I got two solutions there, one to achieve each objective independently. But if I did want a single solution that tries to achieve both of my objectives, I could do that. And here's the single solution that addresses those under the uncertainties. The stochastic optimization and reliability-based optimization builds upon stochastic optimization. It lets you basically put a reliability-based constraint on top of the stochastic optimization. So that's sort of like coupling an uncertainty propagation into the stochastic optimization process. On the subject of uncertainty propagation, we can look at that as well. So in SmartUQ, we would, again, define our distributions for the uncertainties. So here it's being treated as aleatory. But again, if we had something we wanted to treat as epistemic, we could pick a parameter as being epistemic, having epistemic uncertainty. And we select the number of samples to draw from these distributions and make the predictions. We have some tools as well, apart from this in SmartUQ, that you can import the results of into this uncertainty propagation. So if you're trying to determine your distributions from existing data, we have a tool called distribution estimation. We'll take a look at that data, and based on that data, we'll tell you, well, here's the most likely distribution that was drawn from, and then you could use those distributions as the inputs here to your uncertainty propagation. But just to, roughly look at some results here, again, just for kind of some random default distributions I plugged in. Here we see the final output distribution. So we could ask questions of SmartUQ, perhaps we have some threshold value for the maximum stress in the steel that's of interest. Maybe it's 300 MPa. I could plug that in here. And we see that, 4.6% of the time we are exceeding that threshold value under the uncertainties we plugged in. So the topic I want to conclude on here is just covering some of the features SmartUQ provides for integrating with other tools and for automating processes. So I mentioned briefly in the introduction that we have a Python API. So our Python API lets you use any features that I've talked about here of SmartUQ, any of the tools within a Python script. That can also be used to implement SmartUQ within MATLAB. So you can use SmartUQ through our Python integration. We have documentation and support to help you use SmartUQ within MATLAB scripts. We also have the ability to export our models as an FMU. So our continuous response models. So for example, that simulation model or that calibrated model we trained, we can export that as an FMU. And then that can be imported into other tools to integrate SmartUQ models into those tools. So if you're not familiar, the FMU model is a format that is supported by a lot of tools. So for instance, this would allow you to import SmartUQ models into Simulink from MATLAB, Model Center from offered by ANSYS is another tool that SmartUQ customers will use this capability along with, for instance. But there's a lot of tools that support importing of models via FMU. SmartUQ, the GUI that we looked at, can also be linked to simulation tools. So this can make it easier to collect the training data for training models. So the idea here would be you link SmartUQ to the simulation tool, and then you can send a design of experiments, for example, to that simulation tool. The simulation tool runs those cases, sends the results back to SmartUQ ready to train the model. So SmartUQ supports integration with ANSYS Workbench, some MSC tools like Adams View and Adams Car and COMSOL Multiphysics. But if you are using a different simulation tool, or if you have a internal tool that, of course, you don't see listed there, we do have some more generic options available. So something like our SmartSim.io feature would basically let you create your own integration, your own link to the simulation tool or the tool you're collecting the data from to have the same benefits as with those links we've created for the commercial tools there. If you have created one of those links to a simulation tool or to the data collection process in SmartUQ, you do unlock a few additional features. So one of those is dynamic emulation. So this is basically a more fully automated process of training your models, where you just give SmartUQ a target accuracy for the model prediction, a maximum amount of data you're willing to collect to achieve that target accuracy. And SmartUQ is going to follow a more fully automated process of, asking the simulation to collect some data, training a model with that data, deciding if the model is accurate enough, and if it's not, it's going to employ some of our, intelligent techniques like the adaptive design I mentioned before to ask the simulation to collect extra data and then repeat that process until either the desired model accuracy is achieved or the maximum data collection limit is reached. And we also have things like dynamic optimization. This is an optimization algorithm that basically couples the training of the model itself that's being used to run the optimization to the solving of the optimization problem itself. So this can be a tool that's more efficient in terms of the amount of training data you have to collect if your only goal is to solve a very specific optimization problem. So with that, I will conclude things. Again, I do apologize for my voice, and I hope I wasn't too hard to understand just from having this cold. But I'm happy to answer any questions here in the time remaining. Or you can also, feel free to reach out via email if you have any other questions or need any clarifications on what I covered here today.
Thanks, Gavin. That was great presentation we have here today. And we also have those participants' emails, and we will ask them if they have any requests or questions. he can ask us so we can translate it and into English and send it to you too.
Oh yeah, absolutely. Yeah, that would be great as well. Yep.
Okay. So
I'm also
만약에
happy to
요청
answer
사항이나
any questions now if anyone, yeah, if anyone wants to ask a question in Korean and you can translate, either verbally or through the chat box. Yeah, I'm happy to do that now too.
sure. 만약에 질문이나 요청 사항 있으시면 채팅창을 이용해 주셔도 되고요. 직접 질문을 해 주셔도 되고요. So it seems, Gavin, we do not have any questions so far. It seems that Korean is kind of shy people here. So we actually prefer getting those questions through emails. That might be a better idea.
Yep, that's fine with me as well. And I realize sometimes it takes a little time to digest the information and think of questions. So yeah, people can feel free to submit their questions to you via email at any time, and you can pass them on to me, and I'm happy to answer those.
Sure, let's do it that way. We have all the participants' information, including emails and phone numbers. So we will find out if they have questions, and we will translate it and send it to you.
That sounds great.
Okay. Thank you for today's webinar, Gavin. That was great.
Thank you. Have a good rest of your day. Bye.
Thank you. 참석해 주셔서 감사하고요. 말씀드렸듯이 질문 사항이나 요청 사항 있으시면 저희 그 채팅창에 보시면 저희 이메일을 남겨드렸습니다. 거기에 이제 요청 사항을 저희한테 이메일로 주시면 저희가 자세하게 답변을 달아서 혹은 자료를 붙여서 전달을 드리도록 하겠습니다. 그러면 오늘 미팅은 여기서 종료하는 걸로 하겠습니다. 감사합니다.